Hi, we are moving on to a new chapter called fields. Earlier we also talked about field, which include gravitational field, magnetic field, and electric field. And if you try to look at the IB syllabus for this chapter, we'll cover gravitational field and electric field basically. To facilitate your learning and also make your life easier, in this chapter we'll firstly focus on the gravitational side first. So that means we will basically ignore or skip, for example, this one, electric field, and also electric potential, etc. And then we'll go straight to gravitational potential. As a matter of fact, after you finish learning the gravitational part in this chapter, you will be able to understand the electrical side as well. Because if you try to look at the equation on the data booklet about gravitational and electrical, you can see they have put this in the table nicely, and eventually I hope you can also appreciate the beauty of physics and also the beauty of the symmetry of our world. For example, for the force of gravitation, which is something that you learned already in chapter 6, the equation is G m over r squared. As for the force of electrostatic charge, it's very similar. You have a K, which is a constant similar to the big G in universal constant, and the 2Q, big Q, small q, referring to the charge of the two objects. And r squared, again, r remain as the distance between the two charges. As for the other three, you may not know very clearly by now, but then if you try to just compare them, you can find G, the big G, is always, correspond to the K, another constant in electrical, and for mass, it's always correspond to charge in electrical, and same for the distance. All right, no matter how the equation would look like, they are all symmetrical. Very elegant. Without further ado, let's start with the first part, and that is gravitational fields. And this equation shouldn't be new to you because you have learned it in chapter 6 already. And so recall that this is not the definition. The definition is what? G equals to F over m. How much force, gravitational force, you experience per unit of mass at a particular point. So since the gravitational force is given by the gravitational law, which is F equals to big G, big M, small m over r squared, divide by the small m here, and this 2m, which is the object itself or the point mass itself, will cancel out, and therefore you can obtain this equation. And so I don't think we need to spend more time on this for now. Let's move on to another new part, and that is gravitational potential energy. Oh, Mr. Wong, I know this. This is gravitational potential energy, GPE, right? We have learned this in IGCSE already, and the equation is mgh. Yeah, we have learned this already, so we can skip all these things. Not really. Huh? Are you kidding me? Okay. I think first of all, you are too simple-minded and naive. If mgh is simply what we are going to use, then why do we bother to have a new chapter on this? Okay. Secondly, the reason why we have the GPE as the equation of mgh was derived from the first principle, which is work done equals to force integrating force with respect to the distance. And that is why when you try to lift up an object with a certain mass, m, and because when you lift it up, you are against its weight, mg, right? And so going through a distance h, and therefore the object would gain gravitational potential energy of mgh. However, in order to get this to be valid, we have two assumptions. One is that we are assuming on the ground this is the reference, and what we mean by reference would be this is zero gravitational potential. And so whenever you lift up, then you gained the gravitational potential. More importantly, is referring to the weight. It is remain constant. So F is constant. Gravitational force is remaining constant throughout the whole distance. However, if you think about, for example, in the scale of a planet, And let's say this is the point where you are standing there and trying to lift up or even project a certain object to say not that but this distance. All right, if you think about the scale of this, then this is probably like the orbital scale. The weight or gravitational force would no longer be a constant mg. Not like, oh, this is 10 kg and therefore mg would simply equal to 100 Newton. It's no longer 100 Newton as a constant throughout this whole distance. Because you know the gravitational field strength is changing throughout the whole distance effectively. And it is governed by the equation. Again, G equals to big G m over r squared. And of course you can say, oh, when I plug in this small m, and that's basically is the force, the gravitational force you are experiencing. So going back to our first principle, once again, work done equals to integrating the force over the distance. Then now the force is no longer a constant, and that means what you have to do is do a bit of calculus. Gm m over r squared, integrate this with respect to x, or here, yeah, x is referring to the distance from the beginning until the point where you end by its motion. So it will be more sensible to change the r squared to x squared instead. And by using the integration you learn from maths, you should know the expression that you get should be g big M small m over x, and with a negative, and then you may have a distance which is, well, depending, I mean, if you got x2 x1, then you have to substitute x2 x1 like this. And for now, there are two questions that you must ask yourself to clear up the idea. The first question is, where does this x start from? And the next question is, where is GPE, or where is the point when GPE equals to 0? Pause the video now and think about it.
A few moments later.
Okay, the first question should be simple, because if you look at the equation gmm over x squared or r squared, then obviously this must be measured from the center, or the center of mass more precisely, of the planet Earth here. So it will be like this to be x, or these to be x. So here it's probably x1 and x2 like this. And so the next question will be, where is a point when GPE equals to 0? So once again, when you go back to what you learned earlier in chapter 2 or in IGCSE, you use MGH, and well, normally you would set the ground, or the point where you start with, would have a GPD of 0. So whenever, let's say, with this mass, as in 1 kg moving for 1 meter, then you simply substitute into MGH, then you get 1 times 10 times 1 equals to 10, and that is 10 joule you get for this object. But for now, since you are going to use this equation, then probably you should go and look at this equation. So negative g big M small m over x. Again, x is from the center of the planet. And if you want this whole thing to equal to 0, then probably you need to think about what can be done. And obviously, the only way that you can make this 0 is when you have x tends to be, well, not 0, infinity. Okay, infinity. Because only when you define infinity, which is a very, very large number, then the whole number will get close to 0. What does that even mean? Okay, don't worry, let me explain to you. Let's say this is the Earth again, and say here is a line that I draw, and that is the point where it equal to infinity, x equal to infinity. In fact, in reality, there's no line of infinity. And even physically, our universe is believed to be finite distance. There's no like infinite distance at all. But then this is a hypothetical idea where the point from the Earth is going to be infinitely long. And so at this point, as we said, the GPE is going to be 0. And so that means anything that is closer to the Earth is going to be negative. Because think about this, when you have a box of object or whatever, it would naturally got attracted by the Earth. Just like on the ground, if you have an object above the ground, it would just naturally drop by the gravity. So in this process, the GPE would reduce, right? And similarly, if you have a situation like this, then this object in theory should get attracted by the Earth, and so it reduces its own GPE, and so the GPE will be negative. And so let's say negative 100 joule. Okay, I just make up the number. In other words, that means the work done performed by this object is going to be a negative value, and it's going to be negative 100 as well. In another scenario, other than the box going closer to the Earth, you can also go away from the Earth. So for example, if the box somehow go up to this position, just a random position that is between these two, it cannot go by itself, right? I mean, because it should have attracted by the Earth directly. So if this object wants to go to this distance or this position, it must be provided by an external force to push this box towards this position. And that force must have performed a positive work done onto this, right? You have to give energy to this. I think this is very logical. So let's say the energy you get is 75 joule, and so in this case, then the GPE of the box at this position is going to be negative 100 plus 75. That means 25 joule will be the, or no, negative 25 joule will be the GPE that it has. As a result, if you go back and visit this equation again, and if you change x2 and x1 into, say, x1 was infinity, because it's originated from infinity, and then x2 is a particular position, let's say R, then what we get is going to be negative gmm over R minus the negative gmm over infinity, but I can't write infinity, I guess, according to math teacher. So x tends to infinity, and in fact this is going to be 0 anyway. Okay, and that means the GPD at a particular position is going to be negative G big M small m over R. Before we jump into the practice question, I would like you to spend some time to pay attention to the wording of the definition, and you may want to note this down. Okay, so let's look at the definition. So the gravitational potential of two bodies, okay, this is what we have been talking about so far, is the work done that was done in bringing the bodies to their present position from where they were infinitely far apart. So the word infinitely far apart is very important. Bringing it to the present position, alright, is also very important. Okay, now let's try this example. I will first try to show you the naively wrong approach so that you won't make the same mistake, but you have to follow me later on and write down on your notes as well. Hey, it's me again. So let's try to do this, and the gravitational potential energy, we have got the equation, right? Gmm over R negative. That's the energy we need, right? So let's just substitute everything, I think. Okay, so the big G is from the data booklet, the big M is the Earth, 1500 is a small m, which is the satellite mass, and R is simply the distance that you get from the question. And of course, I won't be stupid to forget to change it to meter, so times 10 to the power 3. So let's try to press a calculator and find the answer. Okay, so the answer is negative 1.1 1.148. So let's say 1.15 then, times 10 to the power of 12 joule. So this should be the answer, Mr. Wong. Okay, can you guys find out the problem with this approach and try to rule out the correct approach? Pause the video and try to calculate it yourself.
A few moments later.
Okay, so let me show you the correct approach now. And before that, I would like to show the visual diagram. And this is very important for learning physics usually. Think about this. Say this is the Earth. And now what is said is taken from the surface of the Earth to a certain point. And that is 520 km. Doesn't really matter, right? Above the surface. Okay, and one very important idea you have to understand by this video is, again, this equation is talking about the GPE GPE of a point that was from the infinity. So what you can think about this is you can't simply substitute the R with the separation. All right, R is the position, not the distance of separation. So what you can do with this is you can think about, if let's say, again, this is the infinity, the line of infinity, and this is the object where you bring from infinity to this point and infinity to the surface of the Earth, then you will be able to obtain two numbers, right? One is the position at here, and another one is a position of here. And each of these will involve a work done, involve another work done, 1 and 2, given by the equation negative GMM over R. And if you calculate them separately and minus them, then you will be able to find the difference of the energy that you need carrying from the surface of the Earth to that particular position. In other words, if in the previous approach, if you also try to use 520, because there is also another number about the distance, right? So in case any of you try to add 520 km together with the R, which is 6.38 times 10 to the power of 6 together, you are still wrong. I'm sorry, it's still wrong. Later on, when you see the expression mathematically, then you understand why this is different from the correct mathematical expression. Okay, so let me start to do it. So in fact, we're actually trying to find the difference of potential energy. So I'll put down delta E instead of just energy at a position. So that should be GMM over R, one of them being the new one, which is 520 times 10 to the power of 3 plus, because R is supposed to be from the origin or the center of mass of the planet. So that will be this one plus 6.38 times 10 to the power of 6. Okay, and then minus, like what I said, right? You have to calculate each of them separately and minus them. Minus the negative GMM over at this point. So that will simply be R, 6.38 times 10 to the power of 6. And so when you write this, then you know why this is different from the one that we had only. I mean, this is just the potential energy, gravitational potential energy at this position only, but not the difference itself. Next, if you want to, simply save you some time when you press a calculator, what you can do is you can extract the GMN out. So that's going to be 6.67 times 10 to the power of negative 11 times, well, basically all the things here, 5.97 24 1500, because both terms will have these. Okay, so I could take the negative out even, and then what remaining would be 1 over 5.2, or I can press the calculator actually. So 520 10 to the power 3 6. So this is going to be, wow, very neat number. 6.90 times 10 to the power of 1, 2, 3, 4, 5, 6 minus, minus, because I extracted negative also, minus the one that we had, 1.38. Okay. Alright, so the answer that you get should be something like negative 7055454545. So I forgot to times the negative, so I think the answer will be positive. So I can express it as 7.06 times 10 to the power of 9 joule. Okay, it doesn't really matter like which one minus which one, because the question say difference only. So it could just be an absolute value. But I think mindfully, you should know that this one should have a greater GPE than the other one, because this one is referring to the GPE at a higher position than the later one. Right? The later one is the one that is on the surface, and so obviously with high position, I mean from the Earth, then you have greater GPE, and so the total difference should be positive, because you need that positive work done in order to push that object from the surface of the Earth to that particular position above the surface of 520 km. That's all for this video. I hope you enjoy learning the new stuff and also start to appreciate the invention of calculus, because without that we cannot find the expression of gravitational potential energy in this case, simply because the force is going to change throughout the whole process. Tell me, who invented the calculus at the first place? Guess who is Sir Isaac Newton again? Genius. If you like this video, please hit the like button, and I'll see you again in the next video. Bye bye.